Hi everyone, I'm Brandon. I'm a senior machine learning engineer from Quizlet and working on search and discovery. And today I'm going to talk about Typeahead search. And Typeahead search is literally everywhere. Every time you go to a company, any website, and you see a search bar, and you type in something, and you see multiple suggestions in the drop-down box. That's what exactly Typeahead search is. However, the system might not be perfect. You might not see suggestions at all while you're typing, or the suggestions you see are not irrelevant, or the suggestion can actually slow down your search experience. It could vanish with just a few minor typos, and it could disappear when you type even longer. So today I'm going to talk about a hybrid system that's going to combine the prefix search and the semantic search together. This system is going to be vendor platform agnostic and solely based on open source tools. The system is currently supporting over 4 million requests per day and serve majority of the requests under 62 milliseconds. And with this system, we aim to help the user to type less, and find results faster. And also offer a much smarter way of handling the typos. As in this case, you can see there's a typo in the token biology, but the suggestions are able to correct it. And more importantly, want to help the user to discover the content better, not to abandon the search. For example, here, if the user submit a query, ethnicity is defined as _9.1.3 directly into the search bar, they won't see any direct token matches in the final search results. However, by making relevant suggestions such as definition of ethnicity, we are able to redirect the user to a different but semantically similar query that does have matching content in the final search results. And by reading and studying these content, the user will be able to still answer the original question from their query. So now let's talk about the first component, which is a prefix search. Back in school and in data structure courses, we learn about like trees. The prefix trees is a common approach to look up words, phrases based on prefix. However, this data structure has a very high memory footprint, and you require everything to be stored in memory. And the tree is difficult to split and hard to scale up. In the industry setting, we often deal with 100 million documents, and the common choice is often an online distributed database, which is way more cost efficient and much easier to do horizontal scaling. And to show a little bit about our initial prefix search setup, we gather the historical user query log and generate the prefixes based on them. For example, the query mitosis, we generate the prefix, the first character M, the first two character MI, the first three character MIT, MITO, MITOS, etc., etc. And we put the generated prefixes and their associated queries into this online database table. So during the search time, user type a mito in the search bar. We take over this query and go into this online database table to look up the prefix key to find the exact match. And if we do find a match, then we grab the suggestions, sorted by their popularity, and return as a list back to the search bar. Of course, we need to hash the prefix keys and distribute the hashes evenly across multiple nodes to help us save the latency. With this extremely simple setup, we already see a 15% reduction in search abandonment, a small lift in one-day retention. However, we also see during the experiment, the user only saw suggestion 1/3 of the time, and that signals to us a coverage issue. And let's discuss why we have this coverage issue. And first, we need to talk about an important concept, which is a great query suggestion doesn't guarantee great search results. And that's because the query suggestion system is powered by this prefix data table we just built. But the final content show up in the search result are going to be decided by a different content retrieval engine or search engine. And therefore, it is very possible you're going to click on a very relevant and super popular suggested query, but still see no matches at the end. Like many users come into your platform, assume your platform should have this content, and search for it. And that's how this search query became popular in the first place. But it just happens your platform doesn't have this particular content yet, and they will see no matches, and became like extremely disappointed. And this situation will actually hurt the user experience. And therefore, we can just throw any historical query into this prefix table. We have to use queries that actually resulted in content clicks, because content clicks is a strong signal to us that there was actually matching content in the search results, and that's why the user click on them. However, the issue is, during the past 30 days, we have, on Quizlet, we have 73 million unique queries, but there are only 2.4 million of them that result in content clicks. And apparently, these queries are more popular, and they cover 47% of the searches. If we use this 2.4 million to build this prefix table, we can, at best, cover 47 of the searches. And that also means over half of the searches going to see either no or irrelevant suggestions at all. And what can make this situation even worse is every day we're going to have brand new, non-repeating queries coming to our platform on a daily basis. And that's going to exacerbate the coverage issue. So we know the coverage issue is caused by that when we make a suggestion, we cannot guarantee a content match. So the question here, is there a way we can do better? Is there a way when the users see a suggestion and click on it, we can guarantee there's a match? So the idea is, if we want to have content matches, why not we just put the content titles inside the query suggestion? If so, a user sees a suggestion and click on the title, it's pretty much for sure guarantee they're going to see a corresponding content in the final search results. The idea is good, but we also have over 200 million contents on the platform, and users tend to type up to 25 characters. And that means if we want to build the prefix table to cover all these 200 million content, and each title can have 25 prefixes, that's like a total of 5 billion prefix keys we need to generate, store, and look up. And that's a huge amount of record. And even though we managed to build such a large prefix table, we still haven't solved the problem. Like, what if there's a typo with a misspelling or a special character in the search bar, and they're going to cause the lookup into the prefix key to fail? And now it's a good time to introduce the semantic search, which is going to help us solve the problems above. So in short, semantic search is encode and compare. We have a user query pass through an encoder and convert it into a vector of numbers. We also have multiple documents passing through the encoder as well, and they become the vector of numbers. And now we do compare between the query vector and the document vector. We calculate the Euclidean distance or the cosine similarity distance between every pair of the query vector and the document vector. And based on the distance we calculated and the similarity score, we are able to retrieve the most similar document to the original user query. So to recap, in the prefix search, what happens is we take over the user query in the search bar, go into online database table to find exact match against the prefix key. And if we do find a match, we grab the suggestions and return it back to the search bar. The semantic search works a little bit different. We first pass the user query into an encoder and convert it into a vector of numbers. And then we bring that vector into a vector index or a vector database to compare it against all these embedding vectors that are pre-computed from the potential suggestions we want to make. We calculate the distance between the query vector and the suggestion vectors, and we can grab the suggestions that have the shortest distance or the highest similarities and pass them back as a list to the user. So the two key items here, first, we want to have a great encoder that can capture semantics. And second, we want to have a great vector index that's efficient in storage and can allow us to do fast comparison and fast retrieval. So talk about the encoder first. And Sentence Transformer is an open source library. It has a family of pre-trained models based on various transformer architectures. It's capable to encode the entire sentence, not just single words, into semantically meaningful embeddings. And it's fully open source, available on Hugging Face and PyTorch. And as you can see, here's a table of many different model options. And they have different encoding sentence embedding quality, different encoding speed, and model sizes. And we care about the speed here, which is defined as how many sentences per second the model can process. And we care about the speed because in offline setting, we need to process 200 million content titles. And then in online setting, we need to encode every single query and try to get it down like under 38 milliseconds. So basically, we're making trade-offs between the sentence embedding quality and the encoding speed. And we have decided to use this variant, which is called All-Mini LM L12 V2. And the reason we chose it because compared to this prior model, it's only a slight drop in the sentence embedding quality, but as you can see, it almost doubled in speed. And based on this documented 7,500 sentences per second, it only takes us about 7 hours to finish encode the 200 million content titles and allow us to do the online encoding the query using only 13 milliseconds per query, and that's fast enough. Now since we have this great encoder, and we can talk about the vector index. And the FICE is also an open source library originally developed by Meta to enable fast vector similarity search. And we're going to look at the basic indexes. The table here is the most common popular indexes people use. The top two are exact searches, and the only difference is the L2, which stands for Euclidean distance, and inner product, which is a dot product and similar to cosine similarity. The bottom twos are a bit more advanced. The HNSW is a multi-layer graph, and the inverted file index is a cluster-based. And now let's discuss them in details. First, the exact search. Imagine the entire space. We have 9 documents in total. We already encoded them into vectors, and now we project them into this vector space. Now we have a user query. We encode it into a query vector as well and project it into this vector space. For exact search, we're going to calculate the distance between this query vector and every single document in this entire space. And based on the calculation, we'll be able to find the document that has the shortest distance against this query vector. This is doable when we only have 9 documents in total. But what if we have 200 million? And we have to gonna do 200 million computations. That's gonna be very slow. Now let's talk about the index that will allow us to search much faster. So it's the same document space. We have 9 documents in total. However, we don't jump into calculating the distance right away. First, we run clustering, such as k-means, to generate the centroids. And we mark the nodes with their associated centroids. When we have the query vector, we first compare the distance between the query and the centroids. This helps us to get the closest centroids, the closest cluster against this query. And if we decide we just want to probe into this closest cluster, and now we calculate the distance between the query vector and every document vector inside that closest cluster. And this helps us eliminate the need to calculate the distance against every single document in this vector space. And therefore, the computation will be, the search will be much faster. Let's talk about another index which was also fast. The HNSW is a multi-layer graph. As you can see here, has the 3 layers. And within each layers, there are nodes connected to each other. The nodes also connected across the layers. The second layer is denser than the first one, and the third layer is even denser. During the search, the yellow vector is a query vector. And during search, we start with the top node at the very top of the layer. And we adopt a greedy approach, asking the question, is my neighbor closer to the query than I do? If it is, then we go to the neighbor and ask the same question again. If I cannot find any closer neighbors, then I go down the layer and repeat the same process, going to the closer neighbor and go down the layer all the way until when I reach a point when I cannot go down anymore and I don't have any closer neighbors, then this current node has to be the proximate nearest neighbor against the yellow query vector. To compare between the IVF and the HNSW, the inverted file is a cluster-based, and it trains faster, has a smaller memory requirement. On the other hand, HNSW is a multi-layer graph, and it takes much longer to train, has way more intensive memory requirement, but in return, you get a 1-digit latency and very high recall. And for us, we want to do faster iterations to tune the hyperparameters. As well, we want to have a smaller memory requirement so we can use a cheaper machine. And for Typeahead, anything under 100 milliseconds is totally acceptable. So inverted file is actually a better choice for us. However, still, to accommodate it, like a 100 GB index, even though it's going to cost us $1.89 per hour, but that's still going to translate to over $16,000 total per year. And that's a lot of money. So that still gives us motivation. Can we make it even smaller and make it cheaper? And that's why we're going to apply a compression technique called the product quantization. And the corresponding index name is IVFPQ in FICE. What it does in nature is we have this embedding vector of 384 dimensions, 384 floats. And we're going to divide them into subvectors. And here we have 8 subvectors. And after the division, each subvector has only have 48 floats. And we're going to run this codebook quantization algorithm on this group of subvector. The quantization process is in nature another clustering on this group of subvectors using 256 code words or 256 cluster centroids. After the clustering process is done, we'll be able to use the centroid index to represent the subvector. And therefore, the original representation of 48 floats is now reduced down to 1 integer by using the cluster centroid index. And we run this quantization process independently on each one of the subvector here. So the original 384 floats is now reduced to just 8 integers. And in practice, 8 subvectors is very coarse, right? And we have to use a higher number, such as 32 or even 64. And the 256 code words is only 8 bits, which is the same thing as 1 byte. So the compressed vector will be 64 bytes in total. Compared to the original vector, which has 384 floats, which is 1,536 bytes, that's a compression level of 24. So for an index over 100 GB, we'll be able to get it down to just like 5 GB in total. And that's small enough to put inside a T4 GPU. So for the cost, the original cost will be over $16,000 per year. But now, even using a T4 GPU, it only costs us like $30,000 per year. And that's a 78 reduction in the cost. And finance team, the budgeting process, we're really like this. And now we have talked about the prefix search component and the semantic search component, and let's see how they can work together. So when a user in their browser and type something in the search bar, it's going to trigger a Typeahead search request to our web app, Quizlet.com, which again going to call our internal online inference service. And this online inference service is going to make a parallel request to both the prefix search service and the semantic search service at the same time. Normally speaking, the prefix search is a table, and it returns back faster. If we do get valid, non-empty results, then we will return back to the user right away. We don't wait for the semantic search to come back. However, if the results come back as empty or not valid, this time we are going to wait until the semantic search results come back and take it to user. By doing so, we can overlap the latency between the prefix search and the semantic search, and therefore make the entire system faster. The prefix search is simply an online database table. It's very straightforward. And let's take a deeper look into this semantic search service powered by FICE. In this, we have a Kubernetes container with a Docker image installed, and we have a one CPU and a one GPU. On the CPU side, we use the fast API and a Unicorn worker. It's going to handle the API request and API response. On the GPU side, we have the sentence transformer encoder and the FICE index co-locate, sharing the same GPU resource. The sentence transformer gonna encode the query vector into gonna encode the query into the query string into the query vector, which going to FICE index to look up the most similar suggestions and sorted by the similarity score. And the benefit of using Kubernetes here is, one, we have the volume of the requests going up and the CPU usage start to increase. And when you reach a particular threshold, let's say 70% of CPU, the Kubernetes gonna trigger the auto-scaling policy. It will launch multiple replicas automatically to evenly distribute the request. By doing this, we were able to achieve a stable latency, which is only 25 milliseconds just for this semantic search FICE service. And now let's talk about some experiments we ran. The first one is the control is just the prefix search only with the table. And the variance is a hybrid system we just discussed with both the semantic search and the prefix search. And for the metric, we track it on a session level. So a search session starts when the user click into this search bar. The user types something, and they will start see the suggestion. The user type a few more characters, and the suggestions will be updated along the way. And the user finish typing, and eventually click on one of the suggestions. Of course, they don't have to click on the suggestion, and they might even abandon the search. So the metric tracking here is how often a session has a suggestion click as described here. And we can see the variance has a big lift in the percentage of sessions that has a suggestion click. And also a big reduction in the raw number of the user seeing no suggestions at all during the experiment. However, one thing to notice, we didn't enforce a similarity threshold for the semantic search. We always return the top 6 suggestions. In practice, when you fine-tune the system, you want to use a similarity threshold, such as I only return above 80% similarity suggestions, or above 70%, above 60%, et cetera, to achieve a precision recall or precision coverage trade-off. And the second experiment is about the encoder. we didn't adopt the sentence transformer right away. Actually, the first encoder we did was the universal sentence encoder, which was a TensorFlow implementation published before BERT came into reality. And we used it because it was super optimized for CPU inference. It's already fast on CPU. And sentence transformer has a distilled knowledge from BERT, and does require GPU for faster inference. And you can see here, the universal sentence encoder cannot capture the abbreviation LETRS very well, versus the variant sentence transformer. It does capture this nuance much better. And the LETRS stands for Language Essential to Teachers and Testing Language Essentials for Teachers of Reading and Spelling. So it's quite popular for education platform like Quizlet. And the sentence transformer does provide a better lift on session with suggestion clicks, and also give us a small lift on user actually studied any content from search. So the last experiment, we ran the full system again, and this time equipping this sentence transformer as an encoder. And we see consistent big lift in the suggestion sessions with a suggestion click, and big reduction in number of users seeing those suggestions at all. And also we see a small lift in one-day retention to search. The same user come back to search again the next day, as well as a small lift on company-wide, the platform-wide retention. So not just search, but including other features on the platform. To summarize, in this presentation, we talk about several common Typeahead search problems. We discuss the prefix search component, the semantic search component, and introduce a hybrid system that actually combine the two to work together. And also, we discussed a few experimentation to showcase the impact on coverage, the impact from adopting different encoder, and the impact on several downstream business metrics. And that's all for my presentation today. And hope you learned something from this presentation. And thank you very much.
Thank you.
Any questions?
I have a quick question.
Yeah.
Like you were saying that it was showing the suggestions when you were typing. So is that particularly works? How does that assume is that thing giving the suggestion based on the previous history of the searches that has been happened, or it just randomly shows up something which is start with the same spelling or any suggestions?
So are you asking the suggestion based on the historical user query? Yeah. So it's actually both. We have both the historical query and the content titles. So the historical query coming from the query log, we might, but as discussed at the very beginning, we can just use any user query, right? Because the people can type anything, literally anything in the search bar, like gibberish. So we have to use clicks, the queries that result in content clicks, and that significantly reduce the coverage. And so we combine the content titles as a supplement into the suggestion as well. So when you type into the search bar, yes, you will see sometimes the suggestions based on what other people typed before.
Right.
But also you will see content titles.
Interesting.
Yeah.
So it will not just if we are all in the room and we all are search for something that's going to combine all the search history, not just one particular person, not just my search history, but everyone's history.
Yeah.
That's going to give a suggestion.
Yeah. So it will aggregate the entire query history, not just one person, but actually all the users. So it's not what you searched before, but what other people search and have resulted in successful matching content that they like in the search results. And they are gonna then click into the content, study the content, and fall in love with the platform and stay with the platform eventually. Yeah, no problem.
Yeah. So good. Okay, I have one question. If you go back to the architecture of hybrid search plus the semantic search. Yeah, this one. So you mentioned that most of the time the prefix search will give the response first, right? Compared to the hybrid search. And in case of failure, where it fails to fetch it from prefix search, it will wait for the response from the hybrid search. But in case of if it gives out most of the cases, prefix search will respond first. It runs in parallel. But even if even the response that we get from the semantic search, do you update your prefix search response table from with the output from this semantic search, so that because most of the time semantic search would give a better result anyways, but since it's coming first, the user will get the semantic prefix search first, right?
It will update the online database table the next time when we run the data pipeline. So if the semantic search has a better suggestion, and it will be recorded into our user query log, right? So next time when we refresh the table, it will look at the query log table again, and those records are gonna go into that prefix table.
Okay.
So does that answer your question?
Yeah, sort of. But how do you know? So prefix search gave out a response, and the user goes ahead with that response, or maybe changes the query again to get a better result or whatever, or scrolls and finds the output again. How do you know that they were satisfied and not update the prefix table based on the semantic search's response? Is my question. How do you capture that?
So the question is, how do I know whether the user is satisfied with the prefix search results?
Yeah.
So we use the content clicks as a proxy. So if the user see the prefix suggestion, they click on it,
Yeah.
and later they also click on the actual content.
Yeah.
Then that's a proxy. Yes, this prefix search results is working for that user.
Okay.
Yeah. And this table is not like a static. We use the same table forever. It's a refresh. It's a refresh every month. So it's gonna look at the past month, which query worked for our user, and those query gonna go into this updated prefix table. So it's a dynamic.
All right.
So if I just want to walk through an example, if I'm searching for mitosis, right? You'll hit prefix search, try to get whatever the existing log is in your database, send that back to your front end, and in the meantime, you send something to your fast instance. Now, you're not going to update your UI results with what comes back from your vector suggestions, right?
No, if the prefix search does have a valid non-empty results, then we cancel the request for the FICE.
Okay.
Yeah.
Gotcha. So prefix search comes back. There's something valid there. Does valid just means that it exists or that the user clicked it?
What is the second part? The user click on.
Is validity determined by an entry existing in the prefix search value store?
Yes.
Okay, yeah.
Yes.
So if it exists in prefix search, you don't make a call to your vector suggestions anymore.
It's like when we make the call, we do parallel requests to both services. But if we already have results valid from prefix search, we don't wait.
Yes.
We actually, in Python async, we actually cancel.
I see.
Yeah. We can request.cancel.
Okay.
Yeah. So we don't wait for, basically telling the
Gotcha.
file service.
So you'll never get a response
you don't have to process anymore.
Okay.
We just cancel a request.
Gotcha.
Yeah.
And when you do cancel it, though, on the fast service side, that still goes and updates your prefix potentially, or
in the next batch, in the next time when the data pipeline the refresh pipeline is triggered next month.
Okay, I see. So for the course of a month, the fast service will generate all of these potential queries, all of the results, and then once a month you're updating your key value store.
Yeah.
With
you can think of that prefix table only keep the good ones.
Yeah.
And if the files produce something that is good, then that's gonna go to the table next month.
Gotcha.
Then question is then why do you cancel the process and why don't like the process just run and
Yeah,
store
you
the
can, you
data?
can do
It
that.
is.
You can do that as well. If you cancel the request, you kind of save the computation. So you kind of like decrease the load on the CPU here, versus like you let it run through, then the CPU and GPU still gonna conduct that computation. So it's like, yeah, so
Makes
it's
sense.
like, yeah. So it's like save your computation on your CPU load and GPU load. Especially we only have like one CPU, one GPU here. So we want to be resource conscious. But if you don't, say I have a lot of computation resource and I have a very high budget for the finance, you don't have to cancel it.
Yeah.
Yeah.
Yeah, because I was wondering, like, you're gonna run the whole thing again to create a new database again for the next month. So why not just let it go and store that data for the next month while it's going? But it makes sense because if there's another request, then you wanna do the whole thing again and you wanna save that time. Makes sense.
Yeah. So this is just like a way that can be fast enough, like cost efficient enough. But there's like many other system designs you can try to use. This is not like the only way.
Yeah.
Great, thank you.
Thank you.
All right.
Yeah. Thank you everyone.